Okay, everyone. I'm very happy to introduce our next presenter, Jostein Lima. Jostein holds a master in geophysics from the University of Oslo. He has worked with R&D in the seismic industry throughout his entire career, close to 25 years. He's currently a department manager working on seismic data processing in the compute-to-cloud environment. And he will talk about the recent experience in PGS and what the main differences are when it comes to processing seismic data in the cloud compared to the in-house computer centers. So I will now share with you, Jostein, in a second. And feel free to start when you are ready.
Thank you, Christopher. Can you hear me?
Yes, I can hear you. Thank you.
Excellent. Let's see, and you can even see me?
I can, yes.
Good, very good. Thank you very much for the introduction, and good morning, everybody. I'll talk about what we are doing and in the process of doing when it comes to moving our seismic data processing to the cloud, and how we are able to do it in a financial feasible way. I'll talk a bit about the considerations, and I'll also end with an example. I'll talk a bit about the fundamentals just to set the stage, making sure that we are all on the same page. Why did we choose the cloud? Not an obvious choice. A bit about the challenges we had, how we are trying to solve them, and as I said, we will end with an example. I'm sure there are people here that knows more about seismic processing than me even, but I just wanted to add a bit of introduction so that we are there. So what do we do with the seismic data after we have acquired them? Essentially, very simplistically, we try to reduce the noise in the data as much as possible, which is a process where you use a lot of different tools. Neither of them extremely compute intensive, but there are a lot of different ways you can handle the noise. Then we work on the geometry. Try to make sure that everything is regularized and that we have correct coordinates on everything, which can be quite CPU intensive. Then we are looking into the multiple reflections. These are unwanted features in the data that we want to estimate, and then after we have estimated these features, we can subtract them from the data. This is also quite CPU intensive. Then what we need to do is to estimate a bit about the Earth, and in particular the sound wave velocity, how it travels through the Earth, and build up an Earth model. This can be very CPU intensive. It used to be a fairly manual process back in the day, but as more and more computer hardware has become available, this has been more and more automated, and thus creating a lot of CPU requirements. Then we do a migration, which essentially is moving the data around so that they are pictured in the exact location where they are in the Earth. This is also an extremely CPU intensive process, and then we finally do some cleanup afterwards, which doesn't require that much CPU typically. The combination of all of this, it means that we require a lot of mathematically advanced software. We have this software that has been developed over many years with a lot of code. We have a very high requirement when it comes to CPU, very CPU intensive operations, a lot of storage. Essentially, we are in the petabyte class, even touching on exabytes at stage, but typically projects are in the petabyte class, and we require a very high I/O performance. Just to set the stage, let's look at the computer resources we have in PGS. The latest large investment was back in 2013, 2014, where we got actually a couple of large Cray systems. One of them entered into the top 500 list on the 9th place. So just putting in there to illustrate the amount of compute that actually is required there. We also need a lot of storage. Worth mentioning here is when it comes to storage, it is not all of the storage that we require that has a very high requirement when it comes to reliability. There is a lot of duplication in the seismic data processing and a lot of multiple storage of the data. And in cases where you lose data, it's fairly easy to reconstruct them by just running a process one more time. The Cray has proven to be extremely stable, both when it comes to the hardware and also on the system and software. Impressively stable. It's just running night and day, and we are never losing anything when it comes to CPUs. And it's actually been quite affordable. And you have to take the lifetime into account when I say this. 8-9 years of functioning from a computer is pretty good. Makes it quite affordable. So, what does the cloud give you that we don't have? First and foremost, it is flexibility. It's extremely flexible when you can just almost instantaneously get any kind of hardware, any kind of CPUs. It's really nice, and it gives really a lot of flexibility. Other factors are that you have a high availability, you get lots of hardware, you are moving your cost into a operating cost rather than having to have a lot of capital expenditure. You get very early access to the latest hardware, and you have extremely reliable data storage. I put a question mark after cost because that is not necessarily a given, and I will talk more about that. Comparing this, just to kind of summary in PGS, we basically have only one CPU architecture. In the cloud, you have all sorts of different architecture. Generally, everything that's available on the market. In our computer center, we don't really change the CPU architecture very often. In the cloud, it changes really as soon as you get availability. Our data is stored in not too many files, but the files are really, really big. While in the cloud, the storage is much more optimized for an enormous amount of very small files compared to the files we are. I was touching upon the data loss, and it is not super critical for most of the storage. We do have some storage where it is extremely critical, where the raw original data is stored, but during the process of the seismic data processing, it's not necessarily that super critical. In the cloud, generally, data loss is extremely critical and avoided at all costs. We have in PGS, as I pointed out, the Cray, it's been extremely stable. In the cloud, hardware comes, it goes, you get access to it. It's a lot depending on what cost model you choose. If you choose an expensive model, you have very stable hardware. If you choose a very cheap model, the hardware is much less stable. Speaking of that, on the cost of cloud, it is actually very difficult to get a clear view on how the cost in the cloud is. There is a huge amount of different cost models. And factors that are important in these cost models is what kind of hardware you're running on, even when in the month you're running. You have all sorts of various models you can do. You can have an on-demand model. You can have a reserved such and such many CPUs for a fixed amount of time. You can go out on the spot market, just get the extra overflow capacity, and there is just a huge amount of various options. Honestly can be quite confusing at times. And another important factor is the kind of storage. Back in the days and up until just recently, it was essentially just the POSIX standard that was really the proven standard and the way to do stuff. Later, and what has become very popular in the cloud is the object storage, and this has an impact on the cost. What kind of performance you have on the storage. But one thing that's less available is various types of storage. Generally, I mean there are some exceptions, but generally the only option is what's referred to as the 11 nines. So what are the 11 nines? It is almost 100% reliability when it comes to the storage. A lot of nines after the decimal point. And what does it really mean? I've seen claims that says it's really equivalent that if you have a million objects stored for 10 million years, you could expect to lose like one file. Some says it's really more likely that the Earth is destroyed by an asteroid than really you losing a file. I haven't really gone through and verified these claims, so just put them in there as some examples to illustrate. And what I really want you to take away from this is really the reliability of the cloud storage is extremely high. And what that means is that it also becomes very expensive. it is expensive to have very high reliability. In our PGS and the seismic production processing, we have a much generally a lot less. We use fit for purpose reliability, and depending on what we need. And for vast majority of the data we store, that is generally a lot less reliable, which gives us the opportunity to use a lot cheaper storage. And ending up in this is actually that if you do a POSIX storage in the cloud, it's actually roughly 25 times more expensive than the cost we have in our own computer centers. So what kind of strategy can we come up with when moving to the cloud based on what we have learned so far? Well, it's clear that we want to focus on the really CPU-intensive applications, those that really benefit from moving vast amounts of the CPU. We need to do a gradual transition. The reason for this is that the application may need to be adapted because the environment is so different. Essentially, it means that POSIX storage is really not an option. You need to deport them to use object storage. Even though we move to object storage, the cloud cost is still around 5 times more expensive than in our computer centers. And it's all depending on the reliability there. So it means we need to transfer data back and forth, but nevertheless, it's still a cost and also a performance penalty for us. What it also means that essentially to compete, the spot market it's really where we want to go, and applications, they need to move from an environment where everything is very stable, everything is guaranteed uptime, everything is guaranteed to be present, everything is guaranteed to work, and to another environment where hardware comes, suddenly it's been prioritized so that other companies want to use the hardware, so then hardware moves away, and all the applications, they need to handle it. We have developed a transfer manager to handle really the data transfer, the storage. It's built up by several microservices. We're using Swagger, Python, Redis, and all these modern tools. Run it across several nodes. We have a 10 gigabit internet connection. We do not have a dedicated link straight to a cloud provider. What's interesting is that the strategy we've chosen is because of the focus on the cloud to handle small files. We actually have to chop up our data files in many small pieces and work with those. Then we have to merge them back into large files as well. And this transfer needs to handle both really the seismic data, which are huge files. It also has to handle the smaller parameter files. Algorithm changes. The I/O layer needs to change. Random access is very costly in the cloud, so that needs to be eliminated. Fault tolerance. It's really a key when it comes to supporting the spot market. We have checkpoint data, making sure that we can restart whenever we are losing hardware. have data integrity by checksums, and also making sure that everything is scheduled and handled by the application. Also, swap use wasn't as straightforward in the cloud, so we've put some work into carefully calculate the memory use to make sure that we never run out of memory. It's also something that benefits running on in our own system, because you really don't want to run into to swap. The difference is that in our systems it starts to swap, it goes slow, but the behavior in the cloud is basically the application dies. So I will show you an example and some results from a current run. This was a example where we did an estimation of multiples, essentially estimate unwanted features in the data, and then subtracting them from the data. This was done on a triple azimuth survey outside of Brazil. It means that we essentially have acquired the data with a vessel running in 3 different directions. So you have a triplication of the information in the area. And if you add all these 3 together, it's for around 4,500 square kilometers. If you look at the area that's needed for velocity estimation, it's around 1,500 and a little bit more square kilometers, and then the total finished product becomes around 800 squares. So it's a decent size. It's not of the largest, but it's certainly not of the smallest. In the cloud, we were able to run it for in a couple of days. We used around 3,500 nodes. So that's I think we were around 28,000 CPUs. At the most, since we ran this on the spot market, we lost around 200 nodes or 800 CPUs each minute. Generally, a lot less CPUs than that were lost. And there were also some periods where we didn't lose any node. This is very variable and depending, but the application needs to handle all of that. The area of interest is down here inside this square. So as this was one of the first tests we did, we had a few examples that we ran in the PGS Compute Center, and there's lots of changes done to the algorithm, as you can understand. So we just wanted to make sure that the results are the same. So these are the results, the seismic data from the cloud run. And here I change back to what we have in our computer center. And this is what we have in the cloud. So basically what you're seeing is that there is basically no difference. So that was a good result for us. Some observations. The surface-related multiple estimation, it's somewhat CPU and I/O intensive. We experimented with this. If we used reserve nodes, so that we basically said to the cloud provider that we want to have X amount of nodes for a certain amount of time, and also using POSIX storage. What basically this transfer is to not changing your real application. But then the resulting cost was almost 8 times more than we had in our compute centers. That's something we can't live with. Moving to the spot market, just keeping the storage still as a POSIX storage, we were around 1.3 times more expensive in the cloud than in our computer centers. If we moved to object store, so changing the application, taking advantage of the spot market, using object store, then we are actually touching upon being maybe even a little bit less costly in the cloud, but it's roughly the same. And that's a result we are quite happy with, and these numbers really illustrate what you're seeing if you start by just not adopting the application to really optimizing the application for the cloud, what kind of improvements you see on the cost side. So just to sum up my presentation, it is possible to do seismic processing in the cloud. That works. Results are good. To be financially competitive, you really need to change and adapt, optimize your framework, your algorithms. It all needs to change. The environment is so different. When it comes to storage, having cloud storage for temporary results is at the moment it's just too expensive. Outside of the spot market, our options are low. We see as really the only cost-efficient option is to go with the spot market. We do get a lot of flexibility from the cloud, and as a final comment, although it gives flexibility, the cloud is also not unlimited. So it's when we really want to run the very, very high CPU intensive applications, we would really like to have even more access to more hardware. So that is concluding my talk.
Thank you very much for that. Can you hear me now? Hello?
Yes, I can hear you.
Oh, good, good. Sorry, I had some problems with my computer shut down for some reason, but I see everyone's still there. So, yeah, I'm very happy to see that. Thank you very, very much for your presentation here. It was certainly a bit on the side, but I think this with processing, cluster processing, and being able to run huge volumes is something we see more and more in our current environment as well. There was a question here, Jostein. I'm not sure if you can see. What is the object storage? How is it different between ordinary cloud storage?
I would say that object storage is the ordinary cloud storage. I think that's what it has made into it. The way object storage is different is that it's different from the way that Linux is doing it. It's different from the way all the Unix systems were doing it, where they were using this POSIX standard to be able, and that gives you all of these native calls like file seek and file read and these kind of things, and they are obviously you can still read a file by using object store, but it's actually a different call, and you need to handle it differently. So yeah.
It was also one final question here. How much time do you have in estimates? And I apologize if it was when I was away, but running it on the cloud versus running it on premises, have you done some estimates on that?
Can you repeat that? I didn't quite get it.
Yeah. How much time was saved running this in the cloud versus running it on premises? I guess it has to do with the size and the cluster size, CPU size, etc.
Yes. It was typically we saved. I think it would have taken a week to run in our compute centers, and it took 2 days in the cloud.
Okay, so it's certainly a huge saving on doing it that way. That's for sure. There is a few other questions as well that will.
Yeah, I see. Kjetil Vågbø has a question here when cost of the code base to support the 2 environments, and that is that's obviously a consideration for sure. And I don't really have an exact number on that, but it is for sure something that needs to be taken into account. The bottom geophysics obviously stays the same, but all the handling of the scheduling and these things, we are trying to use some or as much as possible of third-party software, third-party libraries, but it is a cost for sure.
Mm-hmm. Okay, thank you very much again for your presentation. It was highly appreciated that you took time and introduced us to these interesting things.